18 volt, the voltage reduction might happen from 18 volt to 400 volt based on the the charging voltage available at the charging station. And the rest all three are between 400 volt to 800 volt. It's like switchable battery with DC link access. That means you have a DC link capacitor connected across all the components, that is connected together. In that case, you should have a DC link which can cater for both voltages, 400 volt and 800 volt. And switchable battery and broadnet compatibility. This also, it can work for 400 volt fully or 800 volt fully or both. And in case 400 volt fail operational broadnet, in this case the battery should be switched back from 18 volt to 400 volt, or DC can happen in both. So these are some of the different topologies which are HV topologies which are currently ongoing in electric vehicles. So let's go in detail about the 400 volt state of art architecture. So here in this diagram, this depicts only the e-powertrain components, which are I would like to detail only on the e-powertrain components, that is like inverter, motor, HV battery pack, and power distribution unit, onboard charger, and DC-DC. So in every electric vehicle, whether it may be Mahindra car, Tata Nexon, or Volkswagen, or any other car, typically at 400 volt, you will see the electric powertrain components are connected like this in this type of architecture. So you have a front motor and a rear motor connected with the front inverter and the rear inverter, which will coordinatedly drive. And you have an onboard charger available, which will try to charge the HV battery pack. Which and also this socket inlet, it might be of based on the charging interfaces like CCS1, CCS2, or based on any other standards. In case of CCS1, it's only AC charging. It works either single phase or three phase. In case of CCS2, it has AC and DC charging. You can it is helpful for fast charging. And DC-DC converter, which will try to convert your high voltage into low voltage, that is 400 volt to 12 volt, to charge the LV battery. In every car, we have a 12 volt battery, which will be available at the front side. So this battery power is used to power up to start the vehicle, like ignition and inside cabin heater, AC, audio systems, infotainment systems, and outside if you see rear lights, front light, brake lights, all these things, this battery will be supplied. And coming to the HVPDU, it's like a junction box. We typically call it as high voltage power distribution unit, which has a fuse with the input to protect each and every component over here. So this is like a DC bus system where all the 400 volts are connected in parallel with the positive to positive and negative to negative. And this also has some sensing mechanism to monitor the voltage and faults. And HV battery pack, inside the battery pack for 400 volt system, there in the market we have 3.3 volt as a cells. So to make it 400 volt, we connect lot of cells, that is around 110 or 108 cells to make it 400 volt in series. So a group of cells, we call it as a module. For each and every module, we will have a battery management system, and all these are connected in series and parallel, forming an battery pack. In between, we have a manual service disconnect. In case if the battery pack has any failures, you need to open the battery pack. This will provide a safety mechanism for the user, so they can open the battery pack safely, and then they can go for the service. And apart from that, you will have the P relay, end relay, and pre-charge relay. So P relay is called positive relay, end relay is called negative relay, pre-charge relay is used for the pre-charge. So these relays are coordinated together to turn on and off the battery based on the situations. So I will detail about this relay operation in upcoming slides. So this is about, the previous slide was about 400 volt, but the current slide is about 800 volt state of art. In this case, all the components are designed for 800 volt, but there is a possibility to switch between 400 volt and 800 volt, because 800 volt is a very huge voltages when it comes to the four wheelers or truck applications, because in case of four wheelers and truck application, huge amount of currents are involved because of the traction, uh, and it's also, it should be human safe. In that case, what generally the OEMs do is they use two 400-volt batteries, and they switch between 400 volt to 800 volt with with the help of relays or the switches. So if 800 volt is needed, these relays are turned on in a such a way that these are connected series together. In case if it is needed 400 volt for the charging, they are connected in a parallel, and they connect with a DC charger so that to have a fast charging. In case if the charging station is 800 volt, again this will move back to 800 volt system to charge. So this kind of facility will be there for 800 volt, so that the redundancy also can be achieved. In case if there is any one battery goes into failure, but I need to run the vehicle to reach the destination or the service point, so you can move the vehicle into 400 volt by isolating this battery alone, and then you can drive the vehicle. So all these components will be designed here for 800 volt. So this is about HV architectures. And up till here, do you have any queries? I can give some 5 minutes of time for the audience to post their questions. Okay, I think there are no questions here.
Hello, sir.
Yeah, yes, Jagdish.
Yes, sir. Sir, good evening, sir.
Good evening.
Sir, my question is, you're talking about 400 volts to 12 volts conversion and 800 volts to some for the supply of battery.
Yes.
So when you are operating with there's a high voltage, uh, especially when it is in the moving, uh, how about the safety and why it is required, sir? Why we have to go for such a high voltage um, this thing, sir, conversion? Whenever we are working with the 12 volts or 48 volts, maximum 63 volts battery.
Yeah, that is for two wheelers actually. Typically, see, the electric vehicles will, there are different kinds of applications like two wheelers, four wheelers. In four wheelers, we have passenger segment and the luxury segment. And apart from that luxury segment, I will have for truck applications or off-road applications. In case of two wheelers, the battery voltage will be restricted less than 72 volt. But when it comes to four wheelers, because you need to overcome that aerodynamic drag, you need the battery weight itself will come around 750 kg to 800 kg. You need that much kind of energy to drive the vehicle. So that's the reason when we go for higher voltages, you will have a lesser copper losses, and you can meet for the higher speeds.
Okay, sir. And how about this conversion, sir? Conversion efficiency is also matters, no?
Conversion efficiency also matters. Effectively,
If that is the case, what is the what type of motors will be using, and what will be the voltage range for these four wheelers, sir?
yeah, for four wheelers, the voltage range will be 350 to 460. It depends on the battery design, because battery voltage will vary based on the SOC, right? So if you design, if generically in electrical terminology, 400 volt is a nominal volt, but we cannot design the battery exactly for that. But battery voltage will vary with respect to SOC. So the range will be 350 to 460. And the motors which are used currently in the electric vehicles are permanent magnet synchronous machines.
Okay, sir. And this voltage,
Yes.
how about the safety issues with respect to it's a conversion also, right, sir? Battery
Yeah,
voltage will
safety.
be battery voltage, storage voltage is also it is with the 400 volts, sir.
Yes, storage voltage also will be at 400 volt.
Okay, okay. So it is a DC, right, sir?
Yeah, completely it's operated at DC.
Okay. So is it a hazardous? No, sir. DC compared to AC.
Yes, but there are certain standards and process which are involved how to maintain that HV standards, because they are not touch safe voltages wherein user cannot touch it, right? So I have one concept called high voltage interlock monitoring, where in upcoming slides I will be explaining about that topic, how that protection will happen.
Okay. And also, I am interested to know about that 400 volts battery arrangement, how it could be
Yeah,
with
I
the how
will
many
tell
cells will
when
be.
I'm dealing with next slide in the BMS.
Sure, sir. Sure, sir. Thank you very much, sir.
Thank you. Okay, if there are no further questions, I think I can go back and start the other part of the slide. So now let's see about e-powertrain component architectures. When it comes to e-powertrain in electric vehicle, so high voltage inverter, onboard charger, DC-DC, and battery pack with BMS, and high voltage powertrain unit connected together. We call it as an powertrain. In conventional ECU, we call it will be two-stroke or four-stroke or eight-stroke engines called as a powertrain. But in electric vehicle, the power electronic components connected with the electric motor is called as an e-powertrain. So let's see one by one component and its architecture. What are its features and functionalities? So first, we'll see about battery management system. So battery management system is an electronic control unit which is connected to the battery to monitor its energy, to protect it from to protect and to ensure the safe charging and safe driving. Okay, so here, so in case as said, one of the professor asked how the 400 volt system and the battery connected, right? So in the market, we have a lithium ion cell, lithium polymer, or lithium ferrophosphate cells, which are ongoing with the new technologies. So typically their voltages are between 2.7 volt to 4.2 volt. For example, if you take lithium ion cell, the voltage will be between 3 volt to or 2.8 volt to 3.7 volt. So to make this 400 volt, this each cell is connected in series. So 400 divided by 3.8, it will become something around 110 or 120 cells should be roughly connected in series. In that case, it is also not safe to connect all these cells in series in a single fashion. But what generally battery pack designers do is they take a group of cells called around 12 cells or 16 cells. For example, if we take 16 cells as described in this figure, 16 into 3.3, something around 48 volt. So we call it as a module. So we have such kind of modules, 48 modules, maybe something around 8 or 9 are required, if my calculation is correct. So 8 modules are connected in series accordingly. But to make the current compensation, similarly, those cells are connected in parallel to meet the current. So we have different mini modules like 48 volt module, 36 volt module. So are connected in series. For each module, we'll have a CSC called cell supervisory controller or mini PMS, which will monitor each cell voltage, and it will try to estimate its SOC. It try to protect the cell via passive or active balancing. And these, for each module, you will have one cell supervisory controller. So such supervisory controller are connected in daisy chain topology, and then this daisy chain will have one communication protocol, in either it may be SPI or it might be I2C. It is connected to the master BMS. We call it as a BPCM, battery pack control module. So in this battery pack control module, it's also it is also a very high-end microcontroller. So which all features like communications like SPI, I2C, crash detection, coolant measurement, current measurement, voltage measurement, H-wheel, high voltage monitoring, isolation measurement, contact welding, all these things are incorporated. So here each and every module will have one coolant inlet and outlet, wherein the liquid coolant will flow inside to control the temperature. Once all these modules are designed or assembled together, you will have a contactor or a relay unit which are connected here as shown here at the positive end, at the negative end, and the another link, another contactor for a pre-charging. So this is how you protect or turn off or turn on your high voltage based on various scenarios. So in case of fault occurs, this BPCM will get an information via CAN, and it will try to turn off or lift off this contactor so that high voltage is completely isolated. So in this case of BMS system, we have two types of architectures. One is two-box architecture, one is three-box architecture. Yellow color, two yellow colors in the first diagram, you can see it as two-box architecture. Three boxes which are in yellow color here, it's called three-box architecture. The only difference between the first one and this one is high voltage safety detection module. So in this case, all this high voltage safety detection part is involved in the single ECU, that is electronic control unit. But here it is splitted because it's all depends on the decision of the customer, like OEM. We typically call OEM like Ford, Mahindra, all these things we call it as OEM. So they give the requirements for us. So based on their vehicle design and the mechanical part, they will say that you need three-box architecture or a two-box architecture. It might be four-box also sometimes based on the complexities. So then based on the requirement, we need to cater that. So inside the BMS, these are the different features. I have classified the features based on the battery cells, contactors, fuse, cooling, vehicle integration, and safety. So when it comes to cells, cell monitoring, cell supervisory controller will try to calculate SOC, that is state of charge, what is the current charge available in the each cell, state of health, what amount of power it can predict, and it also has some data histograms like three-dimensional charts with respect to temperature, voltage, and current it is consuming currently during charging and discharging, and battery current sensing and monitoring, passive cell balancing. It can also detect the defective cell voltage sensing and monitoring, cell temperatures, because it is also important to monitor the cell temperature. You'll have a temperature sensor like NTC or PTCs which are placed on the cell, and it will try to convert the temperature into voltage. That voltage is given to the cell supervisory controller, and it monitors the temperature. And cell connection monitoring, whether all cells are connected intact or not, and thermal management. As I said, there is a coolant inlet and outlet available. So for the coolant flowing, it has to monitor the temperature of the coolant which is going inside and outside, so that it can try to regulate the temperature of the cells. When it comes to contactors, I say BPCM has to control the contactor control, and once you have a contactor connected between positive and negative, you need to, as age goes, we drive it for 5 years, 6 years, 10 years, so it get ages, it get aging, right? So aging monitoring will also happen, and pre-charge control. So when it comes to 400 volt, it's a huge charge. You have a bulk capacitors connected in the DC link in front of OBC inverter, DC converter. So once you directly connect, it will try to take huge inrush current. So to prevent that huge inrush current, we will connect a series resistor, and we will carefully turn on the pre-charge contactor and try to make the increase the level from 0 volt to 400 volt safely, and then we remove the pre-charge control and we connect the main contactors. So how that happens, we'll see in the next slide. This will be really interesting. And coming to fuse, so in BMS we'll also have a fuse. It is typically a slow monitoring fuse, because when we drive the vehicle, there will be a sudden load or sudden inrush current which happens. For that, the fuse should not blow, so it should be a slow blowing fuse. And fuse age monitoring and pyro fuse firing circuit to detect the crash. And this also BPCM will also acquire the coolant flow, coolant temperature, and coolant control. And when it comes to vehicle integration, as cumulatively as a battery pack plus BMS, it will try to monitor the faults and unified diagnostic services, coordinating with different ECUs, monitoring the supply voltage, and communicating my status, that is BMS plus battery status, to the main control unit or vehicle control unit via vehicle communication and its power management. And when you turn on and turn off, the vehicle should go into sleep mode. That means all ECU should shut down itself, right? So that is called wake up management. So all these things will be taken care. And coming to safety aspects, we typically have cell monitoring, isolation monitoring, interlock, and crash sensing and debouncing. So, and isolation monitoring, because we have 12 volt loads and 400 volt loads, there will be a problem of insulation, right? So you need to continuously monitor the insulation and take necessary action. So we try to measure the measure the resistance between the low voltage path and the high voltage path, and we try to maintain at the particular level. If it is going less than this level, it will indicate insulation failure or high voltage failure. So how this happens, we will see in the upcoming slides. So in upcoming slides, I will focus upon this pre-charge control and isolation monitoring, interlock, and crash. These three parts are really important, which when we need to know about how these are happening inside our power electronics. And coming to BMS, so as said in the previous slide, we have a pre-charge control, right? So we have three contactors, called main contactor as a P relay or a positive relay or a positive contactor. The main contactor negative might be negative relay or a N relay. It names, you can name it however you want, and a pre-charge contactor or a pre-charge relay connected with a series resistor. How it happens is, first we try to close the negative contactor. First we try to close the positive contactor by keeping the negative contactor open, and your energy is available, battery energy is available or battery voltage is available over here, and then we try to close the main contactor. Why? Because when we are trying to close the main contactor, you have a resistor in series. It will provide as a load, so you can prevent the arcing and fast contactor aging. So it is before itself it is loaded. So that's the reason we just try to first close the pre-charge and then the negative contactor, and the voltage will try to raise between 0 to up to 400 volt slowly. This resistor time, how this resistor is designed is based on the RC time constant. By what amount of time you want to have the DC bus voltage to 400 volt. It might be 1 second, 2 seconds. So this requirement will vary from vehicle to vehicle. So generally around 0.3 seconds is needed to come from 0 volt to 400 volt. But in battery side, you will have 400 volt, but DC bus side, you try to build up this voltage slowly by taking 0.3 seconds of time. Pre-charging is nothing but you're charging your DC. When it comes to the capacitor, you cannot directly connect the high voltage or the voltage across it, because you will try to take the huge inrush current. To limit the inrush current and also to smoothly raise the DC bus voltage, we connect a pre-charge resistor. So let's see about interlock monitoring. When it comes to interlock monitoring, as one of the professor pointed out, what is a safety mechanism. He has said how it is followed in the electric vehicles to ensure that all the high voltages are connected together, right? Because they are not safe. So for each and every product, we have this type of high voltage connector, and you can see this pink color one called high voltage interlock loop, which is typically a dead shot over here. So all these components are connected in series, and the return path goes to the ECU. You can see here, like it starts from here, connected. This part will be available here, and this is connected to another ECU. So ECU1 might be onboard charger, ECU2 might be inverter, and these two are connected in series, and finally it goes to ECU3. It will be in the BMS. So this ECU3 will generate a PWM over here, and it will try to receive over here. So this PWM will be processed by a signal conditioning, edge detection, and signal processing by using op-amps and Smith triggers. And this will try to, and the microcontroller inside the BMS will detect the sent PWM is received as such or not. So when you have positive negatives are connected in parallel, these H will be in the series. So this will ensure that all connectors are connected in intact, and ensuring the high voltage are connected together, and gives a safety signal to the contactors or the to the VCU, so that I am ready, so that I can close my contactors and I can build up my voltage, or transfer the voltage from battery to H at the DC bus. That's how it happens. So interlock monitoring is a monitoring the high voltage cable connectors at all components. And interlock monitoring tasks are create the current flow. It might be current or voltage or a PWM. Current and voltage will create a lot of losses, but if you are using a PWM type of signal in this loop, it is very efficient. And measuring the result. Measure the resulting voltage and detect upon the open contactor. Once you assume in case the contactor is open, this loop breaks, right? So there won't be any PWM coming inside for the detection. In this case, what immediately the battery contactors will be open, and the devices will go into active discharge. Your voltage will come down to 60 volt. It's easy, and a human can easily touch and check where the fault occurs. That is open contactor hazard and interlock disconnects first. So I would like to touch upon in isolation monitoring. As said, when it comes to high voltage, it should be insulated, and you have both low voltage and high voltage loads, and there is a possibility of difference in the insulation between the high voltage loads and the low voltage loads. So you can see in this, so typically the insulation resistance is modeled as RC. So insulation impedance is given by RC total by C total. So when the current that is nothing but the leakage current. So if it is greater than 10 milliamperes, it indicates a danger. If it is less than or equal to 5 milliamperes, it is safe. So you will have an insulation monitoring unit inside the vehicle, which will try to monitor this insulation impedance based on the voltage available here, and try to see with the predefined voltage of with the resistance. You will try to estimate the resistance, typically 80 kilo ohm, but it might be 110, 120 based on the vehicle or the needs. So at that case, this will be the scenario. If the resistance is greater than 80 kilo ohm, you are almost safe. If it is equal to, you will be at the level of failure, and less than 40, insulation failure level 2. Here in this case, you will see the hysteresis one. There might be chance of greater than 80 or less than 80 oscillating. When it reaches 80 itself, it indicates the insulation level failure 1. That means all the ECUs, all the electronic components should correct their current consumption, or they try to limit the current, so that to maintain the insulation resistance also to be within the defined limit. So for every 10 seconds, this will be monitored. This will be monitored inside the vehicle. And in case of level 2, it gives an alarm effect, and the fault indicates, and vehicle will automatically stop and go into emergency mode. So insulation defaults may be due to wiring, connections, or internal failures of the system components. So this is about the basics of insulation monitoring. And let's go about the inverter system. So inverter is it's an DC to AC converter. We will try to convert DC voltage into AC voltage, and the AC voltage is given to motor. So motor is connected to the transmission system of the vehicle to move the vehicle from front or back. So in this case, we have LV signal connector, H wheel, and power battery connections. Inside the inverter box, we'll have two controllers. One is main controller and the safety controller. And you have flyback topologies to provide isolation supplies to the gate driver modules, and voltage sensing, current sensing, and also safety logic, wherein in case of any emergency or a failure detects the all the gate driver units should stop the PWM giving to the IGBT bridges. Uh, all these things will be there inside the inverters. And you also have a low voltage supply. That means you have an LV battery wire line, 12 volt line connected inside. This 12 volt is used to power up all the microcontrollers, flybacks, and the signal conditioning circuits which are there inside the inverter. And we'll also have a CAN protocol in electric vehicle industry. All the ECUs are communicated with the CAN protocol. CAN is nothing but controller area network. It indicates that all are connected together. It has two lines. One is RX and TX. One will try to transmit the message, and other line will try to receive the message. So this CAN is nothing but a CAN transceiver IC, and this is connected to the microcontroller. Microcontroller will send some messages via CAN transceivers to the external world, and all these CAN ICs or CAN transceiver wires are connected together, so they can easily communicate and take the messages that are needed. And to have to have the speed control, you also have the motor will have the sensor called speed sensors will be of different types, maybe Hall type, resolver type, and resolver with excitation type. So here I've shown the resolver with excitation type, which will try to give the rotor position angle. So they try to sense the rotor position and excite the power semiconductors accordingly, so that they can achieve the synchronous speed, and also do the necessary action based on the current control or torque control. It can be done. For doing such things, you need to know the motor position or the speed. So in the market, typically motor specifications are available between 200 to 403 volt or 200 to 460 volt, and the maximum currents will be 340 amperes. In case of AC, it would be 340. 340 is a nominal, 425 would be 4 seconds. These 4 seconds will vary. It might be 10 seconds, 20 seconds. In vehicle to vehicle, it will change. And motor specification maybe starting from 60 kilowatt to 150 kilowatt. Here I've shown 80 kilowatt. And top motor speed is 10,390 RPM. Here I showed, but it varies between 8,000 RPM to 15,000 RPM. And the carrier frequency or the switching frequency, which it will be operated not only 5 volts, 5 kilohertz, it will operate between 2 kilohertz to 20 kilohertz. So the functionality supported inside the inverter are by torque electrical and classified into 4 types over here: electrical and inverter parameter calculations. When it comes to electrical and inverter parameter calculation, you need to estimate the torque, what amount of torque is needed to drive the vehicle. RPM calculation, that is speed calculation. Based on the speed, you can calculate the distance covered by the vehicle, and also the voltage measurement, that is DC voltage, and also the phase voltages which are given to the motor, and also the current measurement, and also the temperature measurement of IGBTs, the coolant inlet, and position of the motor. When it comes to safety and protection functions, you should have the limit for the maximum torque limit, maximum speed limit, maximum current limit, and also maximum capacitor control, H wheel signal control, and temperature limit derating, and short term output current limit. Because when you are climbing the vehicle in the hilly areas, so it will take current for a minimal time, maybe 10 seconds to boost up or to take require the torque to move upright. So that is called short time output current limit. And when it comes to inverter operating functions, it might have drive mode management, torque mode management, speed mode of management, voltage mode management. That means either it's typically FOC mode, if in case speed mode, all these things will be available.